All right, 4.1. So we're looking at exponential and logarithmic functions in this chapter. So let's look first in the first section at exponential functions. So an exponential function f with a base b is going to be defined by f of x equals b to the x. So in the exponential function, the x value is actually going to be in the exponent this time. An example, just a quick example problem here where you're just plugging values in. We have the exponential function 42.2 times 1.56 to the x power models the average time spent, f of x, so that's the average time spent, in dollars at a shopping mall after x hours. What is the average amount spent to the nearest dollar after 3 hours at a shopping mall? So we would plug the 3 in for this one here. So we have 42.2 times 1.56 to the third. Okay, now when we're doing exponential functions, we just want to keep in mind the order of operations. And just remember that exponents are going to come before multiplication. Okay, so if I pull up my calculator here and I put this in, I could put this in just like that. It should be fine. But if I'm going to do them one at a time, I am going to want to raise it to the exponent first. So 1.56 to the third, and then times 42.2. Okay, good. I'm glad you can hear. Can you mute your microphone? Because I can hear you in the background as well.
Okay, sorry.
No worries. Okay, so then we get f of x equals, and that was, what was that? 160.21. So that's just a simple one where we're plugging our value in for our exponent. Now, if we're looking at a graph of an exponential function, okay, we have just a couple simple rules here. The domain is going to be all real numbers. The range is going to be all positive real numbers. We're going to pass through the point 0, 1. And we're going to have a horizontal asymptote of y equals 0. So let's look at these two functions in our calculator. So if we go to our y equals button, and let's see, we have 3, and then we'll use our chevron power caret here to the x, so 3 to the x power, and then hit graph. This is what our graph looks like. And we're passing through the point 0, 1 because everything to the 0 power is going to be 1. So we're always going to have that power there. And then let's see here. If I look at my table, this is just 3 to the first, 3 squared, 3 cubed, and so on. So we have that exponential function there. If I look at the function negative 3 to the x, so if I possibly come down here and go negative 3 to the x, that's just going to take that same graph and that's going to flip it. Okay, so think back to the transformations. When we have that negative value in front of our first term or our leading coefficient, it's going to flip the graph over. So let's see here. If I look at this next example here, let's go ahead and put that in our calculator. So we have y equals, I'm going to clear this second term here. And then this is going to be 4. And then it's going to be to the power of x plus 4. So since there's more than one term in the exponent, I do want to use a parentheses here. So I'm going to do parentheses x plus 4. Close that parentheses. And then I'm going to do plus 1. Okay, and that closed parentheses says that this is what the exponent is, and then that's outside of the exponent. So if I look at this graph, okay, here's what I get. So let me move this over so I can copy it on my thing here, see if I can draw this. Okay, so this is going to have, let's see here, we're going to have a point, well, actually I have to look at the table. So if we look at the table on this graph, looks like we're going to have points, well, let me pull this over so you guys can see it real quick. So you're going to have points where it's scaling towards that negative or that positive 1. That's that horizontal asymptote there. And then you're going to have your first point at negative 4, 2. So I can't even read what's on this graph. 1, 2, 3, 4, 2. So there's that point there. And then let's see what other points we have. So we've got negative 3, 5, and then 2, 17. So negative 3, 3, 4, 5, and then 2, I think 17 is like right here. Okay, but basically this graph is going like this. So we're getting, I really cannot draw on this that good. So we're getting close to that negative 1 line, or positive 1, and then we're just going up and up and up and up like that. Okay, so what can we infer here? Let's see, we've got a domain. So the domain is going to be all real numbers again, so negative infinity to infinity. The range, okay, remember that we've got, actually I can draw a line on here. We've got a line, a horizontal asymptote. It is, I don't know what just happened there, hold on. There we go. Okay, so we've got this horizontal asymptote right here that we're approaching at y equals 1. So that's going to be our range, is going to be from 1 to positive infinity. And we're not going to have a bracket there, okay, because we're not actually going to touch 1. We're just approaching that value. And then the asymptote would be this one here, y equals 1. All right, and then let's see what we've got here. Oh, that's all for that one. So you'll just have to answer questions about the graph. And then we're going to look at another exponent called a natural base e. So this is the definition of e right here. So this is 1 plus 1 over n to the n. So everything I plug in for n is going to keep getting closer to this number. So you can actually take a look at that. Hold on a second. If I pull my calculator over here and I go back to my home screen, let's see. If I go 1 plus 1 over, I don't know, 80 to the 80th. That's not a good number to work with. So let's just do 1 plus 1 over 100 to the 100. It's not working correctly for some reason. Okay, so as n gets larger and larger, we're supposed to be approaching 2.71828, but for some reason, maybe because I'm entering it differently. Hold on. What is that? 1, 2, 3, 4, 5, 6 zeros. And then plus 1, it's just getting too small. So maybe we do it with smaller numbers. You guys don't really need to know this. I just like to show you how things work. So if I do this, then I'm going to get closer to this number. This is a number in your calculator, and it's the natural base e. So if you go here, you see in that yellow right there where it's e to the x, where my mouse is. So if I go second, and then I hit this ln button, that gives me that e here. So if I just put e to the first, then it's going to give me that value. So e is a number just like pi. So it's very similar to pi. It's an irrational number, and we call it natural base e. Okay, so the natural base e is a natural exponential function. It's used sometimes in science when we're doing things like carbon dating and population functions. And then we can also be used in some financial calculations. So if I look at this example here, I have the exponential function f of x equals 1066 e to the 0.042x, models the gray wolf population of the Western Great Lakes, X years after 1978, project the population in 2012. So we're going to use this function. We just need to figure out what X is. So we have f of X is going to equal 1066 e to the 0.042. And then x is years after 1978. So for 2012, we would just do 2012 minus 1978. So that would give us 34 years. So 34 would be our x there. And then we're just going to plug that in. You can plug that in your calculator just like that. It should be able to hold that fine. So 1066, then second e, and then it already opens up the parentheses for you. So 0.042 times 34, and then close the parentheses. You're going to get 4,445, and it doesn't say where to round. So I'm assuming since we're talking about actual things, about wolf, let's just round up. So 4,446. Okay, but any test question or homework question should tell you where to round. Okay, and then let's look at what the exponential graph of our e function looks like. So you're going to put that in your calculator just like that. So y equals, we'll clear this. So second e, oops, go back here. All right, y equals second e to the x minus 5. Close that parentheses, and then plus 4. And then we're going to hit graph. Okay, and our e function looks like a normal exponential graph here. Okay, it's shifted up 4 values, so that's where that horizontal asymptote is. And then looks like we're shifting to the right 5 values because of the x minus 5 here. So I can get some points and graph it. Let's see. So -7, 4. So as I'm going to the right more, I'm going up a little bit from 4. Then I've got that 0.55. And then these aren't going to be exact points here. So we just want to get a kind of picture of the graph here. Let's see. If I draw my asymptote in first, let me go ahead and do that. So at 4, 1, 2, 3, 4. Okay, so there's my asymptote, and then let's draw this graph. So we had a point at 5, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we had a point there. That was where the turn happened. So we're kind of going like this. And then we go up like that. So that's what that graph looks like. The domain, again, is going to be just all real numbers. So -infinity to infinity. We've got a horizontal asymptote here at y equals 4. You can see that horizontal asymptote. And then that would make the range +4 to +infinity because I'm going up. All right, so let's see what we have next here. Okay, so compound interest. So this is where exponential models are actually useful in real life. So we've got 2 compound interest formulas, one using exponents and the other one using our natural base e. So here's your formulas. Normally you would have to memorize them, but here they are. So this is what we call periodic interest. So this is when you have different periods of compound. Periodic. Okay, where P is going to be the principal amount. Your interest rate is R as a decimal, so you would convert the percent to a decimal. And then T is going to be time, always in years. And A is going to be the account balance. Okay, so the key word for here, this is going to give you compounding periods. Keyword here is you're going to see this word here, continuous. So that's how you know the difference between the formulas. So for my first formula, I have Jeff has decided to invest $2,345 into a compound interest account. He has an interest rate of 1.65%, but is unsure of what compounding period to select, monthly or continuous. So we're going to do actually both formulas here to help Jeff figure out which account will yield him more money after, let's see, 6 years. 1.65% isn't really going to give you a really big difference, but you should have a small difference here. So our P in this case is going to be 2,345. We have an interest rate of 1.65%. So as a decimal, that's going to be 0.0165. So that's one thing I see students do a lot is forgetting to make that into a decimal. So just try to remember to do that. Your compounding time is going to be for 6 years. And we want monthly. So that's 12 times a year. Okay, and then the other time is continuous. So we'll do the first formula. We'll plug that in. So we're going to get A equals 2,345 times 1 plus my rate is 0.0165 over 12 times per year, and then times or to the nt, so 12 times 6. And then with this one, you want to do order of operations, so be careful here. You're going to go to your home screen, and let's first do 12 times 6. So 12 times 6 is 72. Okay, so that exponent is 72. I need to go inside my parentheses first. So I'm going to go 0.0165 divided by 12. Then I'm going to add 1. Okay, so this is what I get inside the parentheses, 1.001375. Okay, to the 72 times 2,345. So the next mistake I see students do a lot is they'll multiply this first and then raise it to the 72. Remember, in order of operations, exponent is going to come before multiplication. So this needs to be raised to the 72 first. So 1.001375 raised to the power of 72, and then multiply that by the principal. So 2, 3, 4, 5. So that's going to give you $2,588.86. Okay, so that's your monthly amount. Then you want to test to see how much money you would get continuous compounding. So you're using this formula here. So we would go A equals 2,345. E to the, let's see, the R is 0.0165, 6 years. So there's no N in this formula. With the E, you can put that in just like that. So this one's a little easier to do. You just do 2, 3, 4, 5, second E to the 0.0165 times 6. Close that, and then we get $2,589.04. So then which one is going to yield him more money? This one, continuous compounding by, what is that, 15, 14, I don't know, 14, 19 cents, 19 cents more. So if we really care about that 19 cents, then we'll go with the continuous interest. Of course, if you did go with a higher interest rate, then you're definitely going to yield more money. Also, the more money you put in, you'll have more as well. So let's look at these examples as well. So you have an investment of $13,200 for 5 years, an interest rate of 4%, and then different compounding periods. So here you're going to have a principal of $13,200. Our interest rate is going to be 4%. So as a decimal, that's going to be 0.04. And it's for 5 years. So our T is going to be 5. And then we're going to have different compounding periods. So how many times a year is semi-annual? So that's going to be 2 times a year. Quarterly, that's going to be 4 times a year. Monthly, 12 times a year. And then for daily, we use 365. Okay, so this is going to be the same formula, just with different ends here. So for this one, let's see, we're going to have 13,200 times 1 plus 0.04 over n, which is going to be 2, to the 2 times 5. So let's see what that gives us. So we're going to go inside the parentheses, 0.04 divided by 2. Okay, then we're going to add 1. So we get 1.02. Then we're going to raise it to the 2 times 5, which is 10. And then we're going to multiply that by $13,200. So that gives us $16,090.73. Okay, then the next one, we're going to have a 4 for that compounding period. So 13,200, then it's going to be 1 plus 0.04 over 4 to the 4 times 5. So we're going to go 0.04 divided by 4. Then we're going to add 1. Then we're going to raise it to the 4 times 5, which is 20. And then we're going to multiply by $13,200. And that's going to give us $16,106.51. 51. Okay, then for 12, we would have $13,200, 1 plus 0.04. Now our n is 12 to the 12 times 5. And let's see what that yields us. So we're going to go 0.04 divided by 12 plus 1. Then we're going to raise that to the 12 times 5, 60. And then we're going to multiply by $13,200. So $16,117.16. And then finally, our last one, we have 365. So 13,200, 1 plus 0.04 over 365 to the 365 times 5. And then we're going to put that in. So we're going to go 0.04 divided by 365 plus 1. Then we're going to raise that to the 365 times 5. Since I don't know what that is, I'm going to put parentheses, 365 times 5. So my calculator knows that's the whole exponent. Then I'm going to multiply that by 13,200. So I'm going to get $16,122.34. Okay, so as you can see here, the more times this interest compounds, the more money you're going to earn. And the reason why is because it's compounding off of the current amount in the account. So if you add a cent every day, you're going to be compounding off of more money, or $1 every day, etc. All right, my screen is frozen. Okay, there we go. So 4.2. So hold on a second.